Hello and welcome to the third video where we continue looking at problem solving in this topic, turning effect of a force combined with the center of gravity and equilibrium. And today I want to look at the questions which I gave you yesterday. I had asked you to do questions 5 all the way up to number 10, but I've decided to start with the question 4 because I've seen there is a part B of question 4 is a calculation, and part A is a very important concept that we are using throughout. So without wasting time, let's go to the first question, which is question 4, where we are asked to state the principle of moments, and then in the next question we are going to apply that principle of moments in calculations. So, state the principle of moments. What does the principle of moments state? It states that for that system of forces which is in equilibrium, for a system of forces in equilibrium, the sum of the clockwise moments about a given point is equal to the sum of the anti-clockwise moments about the same point. Now, that one's a very important principle, and I'd like you to remember it as such. If a system of forces is in equilibrium, that is a condition that must be fulfilled for the principle to apply. The system must be in equilibrium. That is the condition. Then what does it state? The sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. A very simple but very important concept. Let's look at part B. In part B, we are told that a meter rule of mass 120 grams is pivoted at the 60 centimeter mark. At what point on the meter rule should a mass of 50 grams be suspended for it to balance horizontally? Now here we are going to assume that the meter rule is a uniform meter rule, so that its weight acts through the 50 centimeter mark. Remember, we have not been asked to make any assumption, so that one is an important assumption, that its center of gravity must be at the 50 centimeter mark, that it must be a uniform meter rule for its center of gravity but to be at the 50 centimeter mark. So when you're given a question like this, you will realize that it is not possible for you to solve this question without drawing a diagram. So I'll expect you to draw a straight bar, call it a meter rule, and then you say this is a 0 centimeter mark, this is a 50 centimeter mark, this is a 100 centimeter mark, and then you continue to put in the details as I've done in the next slide. See, I've drawn that meter rule and I've assumed it is a uniform meter rule, so that right at the 50 centimeter mark, that is where we have its weight acting. How did I get this weight? For those who yet don't know, let me just show you how I got the weight from its mass, because it's something that is going to be repeated from time to time. The weight of an object is related to the mass of the object by this equation. This is the mass of the object in kilograms, and this is the gravitational field strength. So 120 grams is the same as 0.12 kilograms times the value of the let me just substitute from the end here. So W is going to be equal to M times G. The mass is the mass of the object. M is the mass of the object in kilograms, and that one I hope you don't have a problem in getting 0.120 kilograms. I've just divided 120 by 1000. 1000 grams is same as 1 kilogram. So to convert 120 grams into kilograms, I just simply divide 120 grams by 1000, and I got this. The value of the gravitational field strength of the earth is 10 Newton per kilogram. And that is what gives me 1.2 newtons. The other method that you can use, I'm going through this because this kind of method is repeated in this question over and over again, is just to remember that 100 grams is the same as 1 Newton. A mass of 100 grams has a weight of 1 Newton. So that again is a conversion unit that you can be able to use. And that is how I got 1.2 Newtons as the weight of that meter rule. Remember, it is acting at the 50 centimeter mark. So we are asked, at what point on the meter rule should a mass of 50 gram mass be suspended? What is this mark here? Is it the 60 centimeter mark, 70 centimeter mark, or let's first of all work out D, so that once we get D, we are going to add it on to 10, and then we get where we are supposed to suspend it. So we are told that it is suspended at the 60 centimeter mark. So this is the 60 centimeter mark. This, remember, this is the 50 centimeter mark where the weight is acting. So the anti-clockwise moment is due to the weight, and it is like that. The clockwise moment is due to this other mass here, which is like this. And that is how I got, how did I convert 50 grams into newtons? I've used the concept which is here. So if 100 grams is same as 1 Newton, how about 50 grams? You'll find that it is 0.5 newtons. So I'm going to take moments about the 60 centimeter mark, or moment about this particular point, and that is where I'm going to get the clockwise moment being equal to 0.5 times how far it is from that point, and it is D. And then on the other hand, the anti-clockwise moment will be 1.2 times 10. In the previous video, we saw that in this kind of substitution, where we are dividing by 100 both sides to convert centimeters into meters, it's as if we never did it in the first place. So that is why it is safe to just use distance in centimeters, although we know moment is force in newtons times distance in meters. So we are going to get this is going to be equal to 12. This one will be 0.5 D, and we're going to see that our D will be 24 centimeters. 24 centimeters. So if this is the 60 centimeter mark, we add 24, we are going to find that this one will be the 84 centimeter mark. Remember, that is what they have asked us. At what point on the meter rule should we suspend that mass? So we are talking about, is it at the 70 centimeter mark, 75 centimeter mark, 80 centimeter mark, 90 centimeter mark? That 84 centimeter mark is a point. It means that this 84 is measured from here, from all the way from here, all the way to this point, it's 84. But what we have worked out is the distance from the 60 centimeter mark to where we must suspend that mass. That is what we have worked out. And then we add that D to the 60 centimeter mark, and we get 84. So don't just stop at working out 24 centimeter mark and you forget what they had asked us at this particular point. That's how question 4 is worked out. Let's go to question 5. In question 5, we are given this. We have a uniform metal rod of length 80 centimeters. So the center of gravity should be at the 40 centimeter mark. And it has a mass of 32 kilograms. So we can convert 32 kilograms into newtons. And by multiplying 3.2 kilograms by 10, we get 32 newtons. It is supported horizontally by two vertical spring balances, C and D. Balance C is 20 centimeters from one end, while balance D is 30 centimeters from the other end. Find the reading on each balance. We have already agreed, when given a question like this one, the first thing you do is draw a diagram. And that metal rod would be represented by just this straight, this rectangular object here. This is a straight metal rod of length 80 centimeters or 0.8 meters. So the balance C is supporting this metal rod at the 20 centimeter mark from this end, and the other one is supporting the same rod at the 30 centimeters from the other end. This is like two people who are trying to carry some luggage, and depending on the position where you are, you may not be exerting the same force, right? So what do we do with this question? And yet, first of all, these 32 newtons, I hope you can remember how I've got 32 newtons. I've just multiplied 3.2 kilograms by 10 newton per kilogram. I got 32 newtons. That is the weight of the rod. And this is the 40 centimeters. If this is 0, this 40 centimeters, and this is 80 centimeters. These 80 centimeters that I've put here means the distance from this point to this point is 80 centimeters. Okay? So the distance from this point all the way to this point should be, to the center, should be 40 centimeters. The weight of the rod acts at the 40 centimeter mark. I hope I'm not confusing you when I talk about the 40 centimeter mark and the distance from this point to this point being 40 centimeters. We are talking about the same thing, only that here I'm talking about this length from here all the way to this point, but when I talk about the 40 centimeter mark, I'm talking about a point. It is 40 centimeters from this other end. This other point here is 80 centimeters because it is measured from this other end. However, the length of the rod is 80 centimeters. So now this question does not have a pivot. You know that triangle pivot, the knife edge, we don't have it. But when we're working questions in moments or turning effect, we can just take any moment about any point. After all, that is what the principle states. The sum of the clockwise moments about a point. It does not mean that we must always have the pivot there. The pivot may be somewhere else. But you are saying, let us take moments about this point. So, which would be the best point to take moments about? Would it be the 0 centimeter mark? Would it be the 20 centimeter mark? Would it be the 40 centimeter mark? The 50 centimeter mark? Or the 80 centimeter mark? Which is the best point to take moments? Now, here is the key. Here is the point that you must always remember. If you're confronted with a question like that one, the best point to take moments about is that point where you want to eliminate a force which has not been asked. You have not been asked to calculate that force, but you feel that it plays a significant part in this question. For example, here there are 3 forces which are acting on this rod. There is this tension here. We can call it tension at point C. That is the reading of the spring balance at point C. The tension in this string at point D, the reading of the spring balance at point D. That is the second force acting on the rod. And the third one is this one here, the weight of the rod itself. There are 3 forces. So, and we've been asked to calculate TC and TD. So, if I were you, I would take moments about point C so that I eliminate the force which is acting through that point. Or I take moments about point D so that I eliminate the force acting through point D. So let's take moment about point C. Moment about point C. The clockwise moment will be due to the weight of the rod, that metal rod, which is 32 times this distance here, and this will be 20 centimeters. This will be 20 centimeters. And then the moment due to TD will be anti-clockwise, and the distance that we are supposed to use will be from here all the way to this point, and that happens to be 20 plus, since this is 10, this will be 30. 20 plus 10. Remember, all this is 40. From here to here is 40. Subtract 30, I get 10. I add that 10 on to 20, I get 30. All right. So clockwise moment will be 32 times this distance here, which is 20. Anti-clockwise will be TD times this distance here, which is 30. And through that, I can be able to get TD. So just get your calculator, work out this one here. This one will be 640 divided by 30. Like that, and you can be able to get that answer. Once you get that answer in newtons, you repeat that same calculation, but this time you take moments about point D. Take moments about point D. So if I take moments about point D, the weight of the rod will tend to turn the system in the anti-clockwise direction. Notice that when we took moments about point C, the same weight turned the system clockwise. So whether a force turns the system clockwise or anti-clockwise depends on the position of the point about which you are taking moments. That one is evident from this question. So when we take moments about that point, therefore we are going to multiply this distance here times 32. That will be the anti-clockwise moment. So we are going to say 32 times this distance here, which happens to be 10, is equal to TC now turns the system in the clockwise direction. When we took moments about point C, TC disappeared from the calculation. Now it comes in. By the way, when we take moments about point D, the force which acts through that point disappears from the calculation, and we already know why it disappears. It disappears because the perpendicular distance from the point to the line of action of that force is 0. Anything multiplied by 0 is just a 0. You can remember that from the previous arguments that we have had. So we're going to get TC times, this is 10 plus 20. Again, that one should be, I think this is 20 plus 10, and we get 30. And we're going to get TC being equal to 320 divided by 30. And we can get that one again in newtons. Just use your calculator, confirm what those values are. Now, there is another method you could have used. Once you got the value of TD, you would just use the second condition for equilibrium. Do you remember the second condition for equilibrium? Yes, the resultant force on that system is 0. What that means as far as this problem is concerned is that the sum of the upward forces, which is TC plus TD, those are the forces which tend to act on the system vertically upwards should be equal to the sum of the forces which acts on the system vertically downwards. So they should be equal to 32. And because you have already obtained a value for TD, it is now possible to work out TC. It's just an alternative method to the method that we have talked about here. So that is how you would work out question 5. Let's go to question 6. You are given a uniform metal rod. Now we are getting used to this. When you're given a uniform length, a uniform object, remember what it means. They are asking you, get the length of that object, divide it by 2, and you know the position of the center of gravity. If you know the position of the center of gravity, that is the point through which the weight of the object is acting. It's just as simple as that. For example, this metal rod here is 5 meters. It is suspended horizontally by 2 vertical strings, P and Q. It's just like the previous question, only that in the previous question there were spring balances. They are the ones which were supporting that object. This time it is just vertical strings. It's the same thing, because in both of them we are working out tensions in the strings. String P is attached 0.8 meters from one end, while Q is attached at 2 meters from the other end. Given that the weight of the metal rod is 110 newtons, calculate the tension in each of the strings. Again, you'll start by drawing the diagram. I've already drawn these diagrams because I really don't want this video to take up unnecessarily very long time. So this metal rod is 5 meters. That means since it is uniform, 2.5 meters, 2.5 meters from either end, we get the position of the center of gravity. Just like we did with the other question, and that is where the weight of the object acts. You can see the importance of drawing a diagram. Never miss that. Draw a diagram all the time. And it's really very simple. Just draw this thin rectangular shape and then put the weight at approximately the center point. Then you draw that arrow to show that that is the weight that you're dealing with. And you know this one's 2.5. So string P is 0.8 meters from this other end, while string Q is 2 meters from this other end. And it is just as simple as that. So to get the tensions in the strings, you'll say the tension in this string at point P, the tension in the string at point Q, and then what do you do from here? Remember, there is no pivot, but that should not be a problem. Just choose one of the points to be the point about which you take moments, in which case now we are going to find that this one tends to turn that system clockwise about that point, while this force tends to turn the system anti-clockwise about the same point, while TP disappears from the calculation. You can see it's just about knowing what to do. The methods remain the same. So go ahead and work out the various values, the various tensions, because whatever I can do here is exactly what I did in the previous question. So I'm really not going to waste time on that part. Let's go to question 7. In question 7, we are given a uniform metal rule of mass 150 grams. You know why we are using uniform. And this is the beauty of it. If you work out these questions, so many of them, you get to understand why certain words have been used. When certain words are used, what you should do with those. Like for example, a uniform body. I've already explained this one very many times, so make sure that you have it. You convert this mass of that object into newtons. You know, this one should give you 1.5 newtons because you just divide by 100, because 100 grams is the same as 1 newton, and it's just as simple as that. Is pivoted freely at the 0 centimeter mark. What force applied vertically upwards at the 60 centimeter mark is needed to maintain the rule horizontal? Very simple. It's balanced at the 0 centimeter mark. This meter rule is Of course, this is the 100 centimeter mark. This would be the 50 centimeter mark. And this is the 60 centimeter mark where this force is exerted. So they're asking us what force applied vertically upwards at the 60 centimeter mark is needed to maintain the meter rule horizontally, or to keep it horizontal, or to keep it in equilibrium. So we apply the principle of moments. What is the best point about which to take moments? It's obvious, it's this point. Why? We want to get rid of the force which acts at this particular point. If we take moment about any other point, we must include this force. For example, if I put my pivot here, for example, let's just imagine we are putting the pivot there. We'll have to think about the reaction force at this point, R, because R tends to turn the system clockwise about this point, while this one tends to turn the system anti-clockwise about that point. So you see, you've got R and F. Both of them are unknown because R plus F is equals to the weight, which is 1.5. Why should you form an expression with the two unknowns if it was possible to form an expression with only one unknown? And that is why we choose to take moments about this point, because it eliminates the value of the reaction force at that point. But remember, in some other questions, that reaction force can be asked. And it's very simple. You just need now, after you have worked out F, you just need to come to this relationship and we work out the reaction force. So this is a 60 centimeter mark. If we take moments about this point, so let me just remove all that, and we can be able to see that since this one is 0 centimeter mark, this is the 50 centimeter mark. This 50 centimeters, because this is a 50 centimeter mark, this is 50 centimeters. So the weight tends to turn the system clockwise about this point, while the force F tends to turn the system anti-clockwise about the same point. So here we are going to have 1.5 times 50 will be equal to what? It will be equal to F times 60. Again, go ahead and work out the value of F. Let's go to question 7. A uniform meter rule is balanced at the 30 centimeter mark when a mass of 50 grams is hanging from its 0 centimeter mark. Calculate the weight of the rule. Again, we draw the diagram and we put all the information there. That 50 gram mass hanging at the 0 centimeter mark will have 0.5 newtons. This is the pivot, this is the weight, and of course we are going to take moments about the 30 centimeter mark because we want to get rid of this R that is acting at this point. So we are going to have 0.5 times 0.5 times, how far is it from the pivot? Should be 30 centimeters, equals to W. How far is it from the pivot? It should be 20. And again, it's easy to work out the weight of that meter rule. You can see how simple these questions turn out to be once you know what it is that you are looking for. Question 9. In question 9, we are given a meter rule is balanced by masses of 2 grams and 16 grams suspended from its ends. Find the position of the pivot. All right. Now, this question, we've not been told whether we are dealing with a uniform meter rule. And even if we are dealing with a uniform meter rule, we've not been asked to assume that its weight is negligible because its weight is not provided for. So in the working out, I would expect that you will assume that its weight is negligible. Its weight is negligible. So that once you put the pivot, of course you will have to realize that if this is the 50 centimeter mark, the pivot must be nearer the 0.24 Newton weight as compared to this one here. The pivot has got to be nearer that particular point. So you're going to call this point O, and you take moments about this particular point. Okay, so as to, you're going to say this is D, so you're going to say 0.24 times D is going to be equal to this one will be 100 minus D, because all this from here all the way to this point is 100, so this distance here will be 100. You subtract D, so it's going to be equal to 0.16 into 100 minus D, and you're going to get 0.24D is going to be equal to 0.16 times 100. We are going to get 16 minus 0.1616D, and you collect the terms with D together, and you're going to get this, I think should be 0.4D, 0.40D, because when you bring it to the other side, you're going to add, is going to be equal to 16, and you're going to find that D is going to be equal to 16 divided by 0.4. Of course, you can multiply here by 10. You can multiply here by 10 so that you get, I think, 40 centimeters. So if this is 40 centimeter, the pivot must be at the 40 centimeter mark. The pivot must be at the 40 centimeter mark. If D is 40 and this is the 0 centimeter mark, then this must be at the 40 centimeter mark, because that is where we've been asked to find the position of the pivot. Let's go ahead and look at the last question, which is question 10. We are again given a meter rule pivoted at its center is pivoted at its center. So this time, once it is pivoted at its center, it does not matter whether its mass has been given or not. We know that the weight of the meter rule is not going to have any moment about that point. A glass block is hung from one end, and the rule is balanced horizontally by hanging masses of 100 grams and 50 grams at the 60 centimeter mark and 80 centimeter marks respectively. Calculate the mass of the glass block. So this is just as simple as that. When you put down that diagram, this is the 50 centimeter mark where we've got the pivot. So the weight will have 0 moment about that particular point. So we don't have to worry about that. We convert the masses into weights. So this one will tend to turn the system clockwise. This one will also tend to turn the system clockwise. While this, the weight of this glass block, will tend to turn the system anti-clockwise. So once you put your equal sign here, the anti-clockwise moment will be equal to mg times how far it is from this point. This point is the 50 centimeter mark, so you're going to multiply by 50. It's going to be equal to 1 Newton times how far it is from the 50 centimeter mark, and that will be 10, plus 0.5 times how far it is from here, and that will be 30. Now, at this point, you can go ahead and work out the G. You work out mg, which is the weight of this glass block, which is the weight of the glass block. In order to get the mass, you'll just need to divide the weight by the value of the G, and you're going to get that mass in kilograms. M is in kilograms, and then it's up to you whether you want to give it to convert those kilograms into grams or leave it as in kilograms. And that is how you are supposed to answer these questions. I hope it has helped you. Go through the video once again, because the more questions you do, the more similar questions you do, the better it will be for you eventually. In the next video, we are going to look at other calculations in our syllabus, so stay tuned.